Hello, my name is Carlos Muñiz Cusa. I am a PhD student from Aalborg University in Denmark, and the paper I will be presenting today is titled Spatial-Temporal Graph Convolutional Network for Stochastic Traffic Speed Imputation. As motivation, let's assume we have an ambulance that needs to arrive as soon as possible to the hospital. The driver has two options, both with the same expected arrival time, route 1 and route 2 as it is shown in the table. The table shows the probability to arrive at 20, 30, 40, and 50 minutes for each route. However, what is the best route? Well, that depends on the uncertainty of the travel duration and the traveler's delay tolerance. For example, if the driver needs to arrive at 40 minutes at most, then route 2 guarantees this arrival time, while route 1 has a 20% chance to arrive at 50 minutes. If we could provide such an stochastic or high-resolution routing service, then the driver will be able to make a more informed decision or a better informed decision. Stochastic routing services are often rely on time-dependent stochastic traffic data representing the speed distribution of vehicles in the road network. Specifically, a speed distribution captures the probability that a vehicle travels at a certain speed range on the segments of the road network. For example, the speed distribution of the segment R11 indicates that vehicles traveling in this segment have 0.4 probability to travel between 0 and 10 meters per second and 0.3 probability to travel between 10 and 20 meters per second, and so on. Given the speed distribution and the distance of each route segment, we can derive the arrival time distribution of each route as we shown in the previous slide. To construct traffic speed distributions for road segments, we can use vehicle tracking data obtained from GPS and loop detectors. However, data collected from these sensors are often incomplete due to technical reasons, such as loop detectors malfunctioning or temporarily unavailable GPS data. This sparseness problem prevents the constructions of time-dependent stochastic speeds for each road segment. How can we find these missing values then? Well, the present paper aims to alleviate this problem. However, achieving a highly accurate estimation model is a challenging task, as traffic speeds in the road network exhibit complex spatial correlations between road segments and temporal correlations between the time intervals. Moreover, the presence of stochastic values add a new dimension in the input data that needs to be considered. Finally, we need to consider the sparseness problem. In other words, the missing values in the design of our solution. Several prior studies have attempted to estimate missing traffic speed values in a road network. However, they either fail to capture both spatial and temporal correlations, for example, only considering a spatial correlation, or focus solely on estimating the average speed values rather than the stochastic speeds. To the best of our knowledge, this is the first paper that tries to solve these three problems. Considering this, we propose a stochastic spatial-temporal graph convolutional network model that accurately estimates the missing speed distributions in a road network. Our key contributions are precisely providing a solution to the previous three identified challenges. First, our framework integrates graph convolutional networks to capture spatial correlations among road segments, and temporal convolutional networks to capture temporal correlations among time intervals in a graph-based road network model. Second, we consider the probability values of each speed range as input channels and learn different convolutional kernels for each of them. Third, to cope with datasets with many missing values, we propose a novel context-aware GCN graph convolutional network that prioritizes the propagation of the observed information in the graph while estimating the missing values. This is the general architecture of our deep learning model, represented as an encoder-decoder architecture. As input, the model received the graph representation of the road network and the matrix representation of the stochastic speed values of the nodes at different time intervals. This matrix. Each row represents the nodes, and the columns represent the probability values associated to every speed range. In the figure, WT refers to the time interval that we want to estimate the missing values, while WT-1 and T-2 are the previous time intervals. As output, the model produces the stochastic matrix corresponding to the time interval T, or the current time interval, with all missing values fulfilled. In general, the encoder learns a high-dimensional representation of the matrix WT, where each probability value is represented as a feature vector that captures spatial-temporal correlations. Concretely, it consists of a linear transformation layer, this one here, that projects the speed distributions into a high-dimensional space, and multiple spatial-temporal blocks that combine temporal convolutional networks, TCNs, and are context-aware graph convolutional networks. More specifically, our TCNs apply dilated convolutional networks to learn temporal correlations between the time intervals. Different from a one-dimensional convolution, TCNs can capture temporal dependencies of more preceding time intervals using fewer hidden layers, thanks to the dilation factor L expressed here in the formula. Note, a different convolutional kernel is learned for each of the input channels, which represent the probability values associated to the speed ranges. In this case, is 4, and we learn different kernels for each of these 4 different speed ranges. Next, we apply the context-aware GCN to learn the spatial correlations between nodes in the graph. Typically, a standard GCN finds localized patterns around a given node by aggregating information from its neighboring nodes. However, in this context, most probably neighboring nodes are missing. Then, aggregating information from such nodes could propagate nonsensical information around the network, resulting in incorrect estimation of the missing values. In the next slide, we are going to explain this in more details. Our context-aware GCN works in the following way. Given the initial representation of the graph given by the adjacency matrix and a context vector storing information about the missing values, in this case, C here, we obtain a directed graph that removes outgoing edges from the missing nodes. We do this by multiplying the adjacency matrix by the diagonal matrix obtained from the context vector. This simple transformation avoids sending unobserved information through the network. For example, the hidden representation of the node E2 is calculated by the weighted average of the observed nodes neighboring E2, ignoring E1 because it has not been observed. The diffusion matrix P contains the weights associated to each node and is calculated using the context-aware adjacency matrix. After applying the diffusion process, we update the context vector C since observed information has reached missing nodes, and the context-aware matrix is recomputed. In general, we prove in the paper that our context-aware GCN places more importance, in other words, higher weights, on observed nodes, hence his relevance in the context of nodes with missing information. To conduct our experiments, we have used 3 real-life datasets with 2,473 and 1,026 nodes. We have used 9 baselines, 5 graph neural networks baselines, 2 non-deep learning, and 2 variations of our method. One considering only temporal correlations, and another that assumes a Gaussian distribution of the speed values and estimates his mean and standard deviation. We use 3 well-known distance metrics for probability distributions, and finally, we simulate different missing values rates, specifically 50, 60, 70, and 80. The box plot shows the distribution of the Kullback-Leibler metric achieved by our method and the baselines. Overall, our method, the most to the right, has the highest accuracy imputing the missing values among all baselines. Specifically, we have from 36 to 50% improvement over GCWC, which is our closest baseline, but does not consider temporal information. This confirms our hypothesis that both spatial and temporal correlations are crucial factors for an accurate model. Similarly, we have 18% to 42% improvement over SST-GCN MV, which assumes a Gaussian distribution of the speed values. This confirms previous studies showing that in practice, the traffic speed doesn't follow a Gaussian distribution, Therefore, to correctly model the real behavior of the traffic, it is necessary to use more precise representations, such as histograms that can model arbitrary distribution. On the other hand, the closest results are obtained by graph weight net baseline. Concretely, we have 4.6% and 7.7% accuracy improvement compared to this method. Overall, we have, for the rest of the baselines, we have from 11 to 35% improvement. We attribute our performance to the context-aware GCN and the explicit learning of spatial-temporal correlations for each of the speed range. In fact, we evaluate further this hypothesis. To do so, we conduct experiments analyzing these two characteristics independently. At the left, we observe that the context-aware GCN is not just good for our method, but incorporating this strategy to GraphWayNet has also rendered an improvement of the accuracy for that method, of that baseline. In general, we found that the context-aware GCN improved the accuracy in 3% in average. At the right, we observed that removing our mechanism to learn multiple convolutional kernels for each of the speed range has a negative impact in the overall accuracy of our method. Specifically, our method loses 4% of its accuracy when we remove this characteristic. As conclusions, we propose a novel deep learning architecture to impute missing speed distributions in the rod network. Unlike prior work, our method efficiently captures both the spatial and temporal correlations in the rod network. We propose a novel context-aware diffusion process that prioritizes the observed nodes in the graph, and experimental results show that we outperform the state-of-the-art baselines on accuracy, from 4.6% up to 50% of the accuracy. Finally, ablation studies confirm our architecture design choices. Thank you.